Good morning, everybody. Welcome back to our statistics course. And after the introduction and after talking about skewness and kurtosis, doing first exercises, we want to come to the next, maybe one of the main topics of this lecture. And this is, in general, the linear regression and also the graphic representation of data. Yeah, what is it about? Well, quite often in statistics, you have some data set. You are asking many people what they are doing, if they like a product, how much income do they have, and then what you want is to identify a dependence between two or later on then more variables. Because in economics, you, for example, interested in the demand for a product, and then you maybe have in mind this demand will, for example, be dependent on the income situation of the consumers. It will be maybe depend on the age of the consumers, maybe the cultural background, and so on. So you can think of many variables which influence another variable. And we will start in the simple situation where we have just only two variables, and then we speak from an independent variable and the dependent variable, and we want to explain the independent variable via the dependent variable via the independent variable. Well, and so maybe we can ask, in some company, you have a data set that you know for X the number of orders. Well, and all these orders may have different volumes in euros. So one order can be a large order with 10 euros, and the other order has only a volume with euro. So maybe these are then days. At the first day, you have two orders with a volume of 36 euros. At day 2, you have 4 orders with a volume of 44 euros. Well, and then you can think of that there is a dependence between the number of orders and the volume of orders. And in general, well, we would expect that the higher the number of orders, the higher is the volume on average. Well, and if we look only at this table, then it is quite hard to directly identify, is there a dependence? The higher the number of orders, the higher is the volume or not. Because, of course, this has not to be the case. And for this, the easiest way to look at this is just that we use a graphical representation. And this is done in the so-called scatter plot that we put on the X, on the horizontal line, the orders, and on the vertical line, the volume. And this would be then, if we take the first data point, 2 orders, and maybe 10, 20, 30, 40, and this would be then a data point just here at 36, and the other one would be 4 orders with maybe 44. well, of course, this you have to do then with all your data points. And for this, I recommend that you should use some software package. So quite often, if you have an PDF file or here PowerPoint file, then you could just copy the data and we put this data then within our software package. And for this, we will do it quite often in Excel, and that you see everything. Well, let's change the width of this. I think 5 is enough. And now you have your data set, and then we want to have orders and volume. And now just use here your possible diagrams, and this possibility here is XY. So this is then the representation with data points. So, and I do it always because then sometimes I'm not sure what is X and what is Y. So click within the data series, data, and then we see here X is order, because you see here this is highlighted right now. So everything is okay. And for the representation, we should then also write down on the X and Y axis what do we find there. So here we have orders. And here we have volume in euro. This we don't need. And this would be then our scatter plot. Well, and if we look at this data set, then of course we would assume that somehow maybe here is a positive dependence between going, oh, no, I changed this. This is directly wrong what I did. So this has to be the other way around. Let's have a look again. Yeah, B is order, so horizontal axis. So I was too fast. Again, axis, plot this volume, and here we have order. Sorry. And now. So that the higher the number of orders corresponds to a higher volume. So from the graphical representation, we would assume that the higher number of orders, the higher the number of volume in euros. But of course, in economics, we are not interested only in the qualitative dependence. We are, of course, then interested in a quantitative dependence. So, for example, because of this dependence, would it be a good choice to hire a new guy in order to increase the orders, maybe? But what is the quantitative dependence? Well, and in order to answer this, there is, of course, no right answer. We cannot say we also see the data is somehow fluctuating. We cannot say this is the right dependence, but we can think of what would be a good choice in order to obtain from a data set a quantitative dependence between these two variables. Well, this we can skip because I did it on the other slide. So, and for this, because later on we want also to calculate somehow the fit, so the linear regression, we use another example where we do not have that much data points, so we can calculate this also more or less by hand. So what we think here is something like the orders. Now it is the visits of the representative ringing at the door of some people and then selling maybe his product. And there we see that we have a dependence between the visits and then the sales volume, similar to the order and to the number of orders and the volume in the former example. Well, and now maybe in this company, they think of, well, should we increase the number of visits? Maybe if we do some investment, hiring new people, for example. But what does this mean? What can we then expect in the development of our sales volume? And for this, we want to apply these historical data which we have in our company. And this is quite often the question, that we want to extrapolate the dependence which we assume from our data and then hopefully obtain in this case, for example, a positive dependence, so that we maybe can assume we can also pay a new hired people. Well, and for this, we want to introduce now the theoretical concept of linear regression. So the linear regression wants that we want to analyze quantitatively the dependence between two variables. And for this, if you remember on school, mostly you put on the vertical axis the variable y and on the horizontal axis x, and then we call this one the dependent variable and x the independent variable. Well, in school also you quite often just wrote on the vertical axis f of x, some function. Well, and for this we call x is explaining y. And this then means that if we change the explanatory variable, that this will also induce a change of the explained variable. And very surprisingly, if we call this linear regression, this functional dependence between y and x should be very simple, because it should be just a linear function. And I think you dealt also with your introduction courses in mathematics with functions, and there of course also with linear functions. So an example, f of x equals 3 plus 2x, and this would be the cut at the vertical axis, and this is just the slope of the line, or in general, our linear function is defined by two parameters, a and b, and the cut at the vertical axis, and this is just the slope. Well, such a function looks like maybe this one is maybe then f of x equals 3 plus 2x, but we can also think that f of x is maybe, let's say that this is 8 minus maybe 1.5 times x. Well, and if we go back to our first example, then what we want to do now is to find for the linear regression, find a, in quotation marks, good linear function in order to fit the data. And for this, we have to talk about what do we mean by good. Well, in this case, a good fit would be quite easy, because what kind of function would you fit if you see these data? The red one and the blue one. Yep. Yeah, because here we see if we take the blue one from 2 to 3 and going up 3. And this is always the case. So we have here always the same steps. So going down 3 and 1 left, going down 3 and 1 left would then mean that this, of course, would be our best fit. Well, and then we see we are cutting here at the vertical axis at 2 and going 1 to the left and 3 upwards then just means that we have a slope of 3. So in this case, f of x would be just 2 plus 3 times x if we say that this is x and this is y f of x. Well, and I sketched this data just also for the negative slope. Here we are going down 1 and 2 to the right always. So we also know that all data points are lying at 1 on 1 line. Going 2 to the left and 1 up means we cutting at 20, and then hopefully my drawing will be okay. That this would be then f of x equals 20 minus, and now we are going 1 down and 2 to the left, and this would be then what kind of slope? 2.5? 0.5, yeah. So 1/2 times x. You're right. Well, in this case, if every data point is lying directly on a linear line, then I think we do not have to talk. Further, it is clear what would be the best fit for our data. But of course, in general, this won't be the case. And well, if we take our example, then this is the scatter plot of our example here. And then we, of course, see, well, the data is not lying on a linear line. Well, and then if we do this more or less by eye, maybe you can also maybe try for yourself just one fit. Let's say I try this one here. So fit by eye. Well, and what we are doing if we are fitting by eye, maybe you can describe. How do you, if I just ask you here, fit a linear line by eye, what are your implications? What you are thinking of? How should I do it? Yeah, definitely. So I think a good choice in general, if we ask 100 people, they would then say, well, somehow maybe some data points are lying on the line directly and the other ones shouldn't be that far away. So somehow we have a look at these distances. And then let's take also another color. this is then my first choice. Another one would maybe take a line like this, and the third guy would maybe take a line like this. So, but always it will be the case that we keep in mind the distances of this fitted line with respect to our data points. So, the question is, how should we calculate, black again, this regression line? What would be good choices for the two parameters, the cut of the vertical axis A and the slope B? Maybe let's have a look. If this was my first fit, then this is maybe 1.5. And what kind of slope do I have if I take this one here? So this is 5, and I'm going up a little bit more. So this is 35, 5, 10, 10, maybe this is delta y is roughly 12. So my fit by I would be then f of x equals 1.5 plus 2.4 times y. So, and now we come what we are in general are doing when we are doing it in a quantitative way. Well, if we would know these two parameters, then of course we also know these distances. So these distances are the difference between the data point and this is corresponding point on the fitted line. And this would be then a reasonable choice to look at these distances. But of course, we have to keep in mind if we are using another, so if I do not use this black line but the green one, then of course all distances are changing, or almost all. So we are interested then at every single distance, and somehow we have to keep in mind then for a good fit that all distances together are more or less small. And what is then the mathematical choice? Well, then we are going to the case that we say, of course, maybe we sum up all distances. But if we only sum up all distances, then of course here y hat minus y is positive. And if we take this point, so in this case y hat minus y is larger than 0, and in this case, y hat minus y would be smaller than 0. So, and then, of course, just summing up all differences, I think you would agree, would not be a good choice, because then, again, all the differences would or could cancel out. Well, and because of this reason, we could say again, well, let's take the sum of the absolute value of all distances. For this reason, summing up all distances would not be a good choice. So maybe the sum of all absolute values would be a good choice. So possible function would be sum over all yi minus y hat I. To be minimized. But in general, we use the sum of all squared distances to be minimized. So this function. I from 1 to n, I from 1 to n. Well, and again, we talked about this when we were talking about the variance. Why do we choose this one and not this one? Well, one problem which we do not have also when we use the square is also the problem of the sign, because the square of a negative number is also always a positive number. But this problem we got rid of also by just taking the absolute value. But in this case, we have a function. Again, let's take f of x is x squared. How does this function looks like? This was a parabola, and then within the minimum, the derivative exists. The derivative exists. So this would be then something like a practical reason, because if we compare this with the absolute value function, then we have f of x is absolute value of x, and this has just a kink in the minimum. So while there we have two derivatives, -1 and +1 in the minimum. Right and left derivative are not equal. So maybe this is just a practical reason, since we want to minimize something. Then when the derivative is existing, this is much easier than if it's not existing. But what else could be the reason? So this is maybe one. Second, remember the normal distribution. And for the normal distribution, the density function was roughly a 2x minus x bar squared over sigma squared. And here, within the normal distribution, we have also the squared distance. And quite often we assume that these differences here, this can be more or less interpreted as the error we are still making when we have fitted a line. Because not every data point is lying on this fitted line. And then, if we do not have any idea about the distribution, we quite often assume that these errors are normally distributed. But if they are normally distributed, then they are represented via this density function with the exponent where we find these squared distances. And quite often we assume that the error are normally distributed. Well, and then, I don't know, does anybody of you have the topic maximum likelihood estimation? The internet? Do you have? No. Okay. But when the guy who has the maximum likelihood topic, then there's also the reason that if the errors are normally distributed, that Then the maximum likelihood estimator is just the best estimator with the squared distances. And third, if epsilon or r normally distributed, then the minimum of the squared distances is the so-called maximum likelihood estimator. And there I refer just then to the topic of the term paper. See one topic of a term paper. Okay, so at least we have then more or less 3 good reasons not to use the absolute value, but to use the squared distance. But you have to keep in mind, there can be, of course, situations where it is better not to use the squared distances, but another function to minimize. So only because most people use the square distances, you should always, if you're analyzing data, always pose the question, in my case, is it also a good choice to use this? Well, we have here some general reasons why it will be quite often a good choice, but keep always in mind that it could be also better in some cases to use some other function. Okay, so if we now take these quadratic differences, then identifying this function, then we have to ask, well, how do we obtain then our 2 parameters A and B for our regression line? So what we have to do then is just that we take our data points yi and xi, and we feeding in our hypothetical linear line now our data from the independent variable x, because this is nothing else than y hat I. This is our regression line. So this together is then the error squared. Well, remember, all xi, yi are known. This is just our data set. If we go back to our example here, So this would be then x1, x2, x3, x4, x5, x6, y1, y2, y3, y4, y5, y6. This is all known, so these are not any variables. So what we have here is just a function depending on these two variables a and b. Well, and if we have a function depending on two variables, in order to minimize or in general to optimize such a function, what we are doing mathematically, any idea? Yep. Yeah, dx over dy. So it is the derivative. You are looking for the derivative of the function and setting this derivative equal to 0. Because then remember this case here, x squared. This looks like this. So here in the minimum, we have just a horizontal line for the slope, and this is then the minimum. So what we are doing then is df with respect to a and setting this to 0. Well, and this we are doing now. Well, this looks quite complicated here, but remember, x and y are all fixed numbers. So what do we have then here if we take yi minus a minus plus bxi squared? This is nothing else than y1 minus a plus bx1 squared plus y2 minus a plus bx2 squared and so on until yn minus a plus bxn in brackets squared. Well, and then you see in every part we have our a and b. Well, and if you have to calculate the derivative of the first part with respect to a, what is it then? Just take the derivative of this part. You know, this is a fixed number and this is a fixed number. Maybe as an example, let's say this is 3 minus 1 plus, not this we are interested in, sorry. A plus b times 2 squared. And this is now a function f of a. What is then f prime of a? Yep. Mm-hmm. 2. So here we have a function where we have an outer function in brackets what we are squaring, and then we have the inner function where we find the a. So maybe in school you have done things like this. F of g of x would be, for example, x, or let's say 3x plus 1 squared. then f would be just the squared, and g would be just 3x plus 1. And what you have to do then is to take first the outer derivative, and this I think you already mentioned. So this would be then 2, but times the inner function. So we still have then 3 minus a plus 2b. And now we have also to take the inner derivative. So 3 minus a plus 2b we have to derive with respect to a. Well, this is just only one number, but with this minus sign in front. So as an inner derivative, we only just obtain this minus sign, because this is more or less f of a equals minus a. All other things, b, when we take the derivative with respect to a, is for us just a constant, and the 3 is of course also a constant. So, and this we have to do for all parts. It is always the same what we are doing, so in the end we still have our sum. So we obtain minus 2 times now just the inner function yi minus a plus b xi, and this has to be 0. Well, if we take the derivative with respect to b, then we have to look at this part here. Again, the outer derivative, 2 times yi minus a plus bxi. Oops. But what is the inner derivative of this part here? If you say that f of b is b times xi, what is then f prime of b? Remember, this xi is again just a number. Maybe it's 3. What is then the derivative? Idea? So if we think, you also think b times 3. What is then f prime? 3, of course. So, and our 3 is just our xi, so the derivative is just xi. I know this is a bit tricky because in general we always think x is the variable and then we are a little bit confused. But you have to change in your head. Now my variable is b and x is just a fixed number, so I end up just with xi. And now I have to be careful, since xi has also this index of the summation. I cannot take this inner derivative outside the summation because I have to sum up over all xi. So, and therefore this has to be in front of the brackets from 1 to n and from I1 to n. So, and what I have here now, again, keep in mind, x and y are all just known numbers. What do I have here now is just a linear system. There's no squared anymore. And two equations. Two equations and two variables I'm interested in, A and P. So this is a linear system with two equations and two variables, A and B. Well, I think this you have done in school in class 9 or 10, and hopefully you have done this also in your introductory course in mathematics. Because very, very often we approximate processes in companies, in economic situations, just with linear functions. I think most of you have entered my macro course and remember, for example, the consumption function in the Keynesian model. There we also said we had just an autonomous consumption, not depending on income, and then plus marginal consumption times the income. This was also just a linear line. And I think most of my examples I gave you were just linear lines. Well, and for this we know that this we can solve in general. And this can be solved in general. Well, we could now also prove the existence of the solution, but yeah, maybe heuristically we can just motivate that there is a solution by looking at this squared function. So what we have here is somehow a three-dimensional quadratic function because it is quadratic in A and B. And what you then have is more or less something like a pot in 3 dimensions, which looks like just like a function of f of x is x squared. And then what we are looking for is just the lowest point in your pot. Okay, but then this I think we can do today. Let's start with 1 and look. If we look up this function here, then we see that we have 2 times the sum. So we can divide left and right side by 2. Here we have a 0 and nothing else changes. So this translates then in 0 equals sum over yi minus a plus bxi. Well, I omit now this index here. Well, this is now just the sum over 2 linear terms. And from this, we know that we can split off the summation. So this is then sum over yi minus the sum over a. This is a minus bracket, so this is also the same as minus I minus bxi. So minus sum bxi. Well, what is this? The sum over all y data points. Remember, the arithmetic mean of our y data points is nothing else than 1 over m times the sum of all data points. So this is then nothing else then n times the arithmetic mean. A is a fixed number, and this should run from 1 to n. Remember, if we take, for example, sum over I equals 1 to 3 over the number 4. What does this mean? This means nothing else than summing up for I equals 1, 4, I equals 2, plus 4, and I equals 3, 4. So this is then 3 times 4. This is also just a fixed number. Summing up from I to 1 is then nothing else n times a. Well, we also know 3 times xi. I1 to 3. This is nothing else than 3x1 plus 3x2 plus 3x3. So we can take outside the 3, x1 plus x2 plus x3. And this is then 3 times sum I1 to 3 over xi. So we can take this parameter just in front of our summation. So this is b times sum over xi. But remember this and look at this. Of course, also x bar is 1 over sum over xi. So this part here is then just n times the arithmetic mean of x. So we obtain minus n times b times x bar. Is still equal to 0. Well, if this is equal to 0, then we can divide both sides by n, and we obtain y bar minus a minus bx bar equals 0. And this we can now solve just for a, that we have a equals something. So putting a on the right side, we obtain a equals y bar minus bx bar. And there's already what we can see from this condition, a nice result that we see here, although we at this step we don't know a and b, we already see that the data point represented by the both arithmetic means of x and y is lying on our regression line. So from this, we already see that the point x bar, y bar is lying on the regression line. Well, let's take this at first. Oh, here's a minus missing, sorry. And let's move now to 2. Here we multiply at first just our bracket that we obtain now, and of course we can also divide by -2, that this is vanishing. So we obtain here, multiplying this bracket is xy, yy, minus xy times this bracket here, so it is xi times a, and minus xi times b times xi. So minus b times xi squared. Well, and now we split also this sum, because these are all just different parts, so we can just write in front of every part the summation sign, xi, yi, minus sum xi times I minus sum bxi squared. So, and now we just feed in our A, which we obtained from this condition. So what we then obtain is with star, we obtain some xi, yi minus and this A is again just only, or let's go one step backward. Sorry. This is again just a sum over A times xi. From this we know again this is n times our arithmetic mean. So this is then A n times x bar, and here we can also move the fixed parameter b outside the summation, xi squared, and now we want to feed in our condition. So we obtain xi, yi, and now we put in for A minus y bar minus b x bar, this is A, times n x bar and minus b sum xi squared. What we are interested is in the end that we only want to have b is only dependent on our data set x and y. So we go further, xi, yi minus, and now we multiply this bracket. So n y bar x bar minus times minus is plus. So plus b, here we have an n also, n, and x bar, so x bar squared minus b sum over xi squared. Well, and then we see here we have in these two parts our b, so we can move out the brackets, our b, so we obtain sum over xi yi minus n times y bar x bar plus b times from the first one n times x bar squared minus sum over xi squared. And this should be still equal to 0. So in the end, we put this part by taking minus, subtracting this on both sides on the left side. So we obtain n times y bar x bar minus sum over xi yi over n times x bar squared minus sum over xi squared equals b. And this is only dependent on our data set. Within here, we see that we only have x and y and the amount n of our data set. So this is then just a number. And let's see, I think I take this, copy, and this doesn't function. So, and if we have our b here, this we can calculate directly from the data set. Then we can feed backward this b in here. X bar and y bar are also known. So from this condition that x bar, y bar are also lying on our regression line, we can then backward also calculate our parameter a. Well, here are also the conditions, the calculation we have done on at the other slide. This we can then also skip. And if we put all things together, then we end up with these formulas, and hopefully I've done it here right. That, let's see if this is right, what I've calculated. Yes, I don't need. So what do we have here? This part we have here, sum over, oh, I did it the other way around. How can I show this? Well, if I divide both sides by 1 over n, then I see that this formula just equals this formula here, because then this n and this n cancels, and xin, and we end up with these formulas here. Or, oops. No, other way around, I have to take out the n here. So this is then, in order to be correct, this can be then written as n times x bar x2 minus 1 over n sum xi yi over n times x bar squared minus, what do we have here, 1 over n xi squared. And this condition here we already showed, and this we will show then in this exercise, and that these are also the same. And about covariance we will talk then later on. Okay, and then next week we will do our calculations just with our example. So then, thank you very much for today.